All right, hi everyone. I hope everyone can hear me. If you can't hear me, wave your hand, please. Okay. So my name is Andy. I'm one of the TAs for this class. Professor Roth is not around, so I'll be filling in for him today, and we'll be talking about evaluation. So a couple of announcements. We have office hours. So if you go to the class website and you click on the staff link, you'll see all the TAs. There are 9 TAs, and you see their office hours and where you can meet them at those times. And so I think most of the TAs have locations on office hours, but there's I think about 2 TAs who don't have office hours yet, and in the next couple of days we'll figure that out. So I encourage everybody to take advantage of that, especially now that you have homeworks, and yeah. And then we have recitations at 3401 Walnut Street at room 401B. So we meet on Tuesdays and Wednesdays. On Tuesday, we meet at 6:30 to 7:30. And on Wednesday, we meet at 5:30 to 6:30. So last week we met and we covered like the basics of Python. And this week we'll be talking about decision trees. So again, I encourage everybody to come out and attend this recitation. And then homework submission. So we made like a few changes to the submission instructions. So the homework is still the same, but you should look at the way you should submit your homework. It changed slightly, and I think we posted it yesterday. So that's that for announcements. Anybody have any questions regarding the announcements? Yeah.
Can we have the slides uploaded before the class?
The slides for which slides? This will have to be uploaded after the class, though. But maybe in the future we'll upload it before the class. Yeah. And then something I missed. So for the recitation, whatever we cover on Tuesday, we're going to cover that on Wednesday. So if you can't make it to the Tuesday session, we're going to cover the same thing on Wednesday. So you can come to whichever one you want. You don't have to come attend both. So I'm going to stand here. It's a little weird. I can't see that properly. Today we'll be talking about evaluations. So there are different stages of machine learning. So first of all, we're given like a label training data where we have the input X and the label Y. And there's a function that maps X to Y. And so we're supposed to train a model that can approximate that mapping between X and Y. And once we train the model, we're now given an unlabeled data set, and we're given X and we want to predict Y. And so these are the different stages of machine learning. So after this, it's important to measure how well your model works. And so there are different metrics that are being used to measure how well or the performance of these models. One of them is accuracy. So accuracy is essentially the number of correct predictions divided by the number of test instances. And the error is 1 minus the accuracy. So that's essentially the number of incorrect predictions divided by the number of test instances. Another metric, it's precision and recall. So recall is essentially the ratio of number of relevant records retrieved to the total number of relevant records in the database. And we'll see examples of this. And then precision is the number of relevant records retrieved divided by the total number of records retrieved from the database. And precision and recall have an inverse relationship. So recall rises as precision like declines and vice versa. So this is another metric. So confusion matrix is essentially a table that describes the performance of a classifier or model. And so So the TP is essentially, it means TP just signifies that the label is yes and you predicted yes. And that means true positive, and FN, which is false negative, just means that your label is yes and your model predicted no. And the same follows for FP and TN. FP is false positive, and TN is true negative. And so we can actually calculate the accuracy by using this table. So the formula for to calculate the accuracy is TP plus TN over, so P is the number of positive instances, and N is the number of negative instances. And we'll see an example in the next couple of slides. We can also calculate precision that we talked about a few slides ago. So the precision is TP divided by TP plus FP. And the recall is TP divided by TP plus FN. So this slide here shows an example. So there are 165 instances, and you have TP is 100, FN is 5, FP is 10, and TN is 50. And so from this table, we can calculate the accuracy, precision, and recall. And if you see down there, the accuracy is 0.91, the precision is 0.91, and the recall is 0.95. And we essentially use the same formulas from this slide. Any questions so far?
Can you go back a slide, please?
Yes.
For accuracy, that equation at the bottom, is it the denominator should be negative and positive, or is it just negative?
Let's say that again.
For that accuracy equation, it's equal to n over n.
That's divided by N.
Is there another cell where the p?
Yeah, so N is the total. So, sorry about that. So in this slide, P is the positive instances and N are the negative instances. And both of them, if you add both of them, it's N. And that's why we use N in that other slide, yeah. So that's the total number of instances, yeah. And then here we talk about training and test data. So usually when you have a data set, you want to split it. You want to use part of it as test and part of it for training your model and part of it for testing. And the most important thing is that you want your model to perform well on test data and not just necessarily on the training data. So it's important that your model it generalizes. So you want, like I said earlier, you want that your model performs well on test data. And if it performs better in training data, that's not good. So this slide here just shows on the left-hand side, you can see your full data set, and you can split it. You split part of it for training and part of it for test. And so you want to train your model on the training data and test your model on the test, use the test data to test your model. And so this slide just shows a decision boundary, a simple decision boundary that is able to figure out the different data, to split the data. So even though there are overlaps, but this is actually better than say this one. So this decision boundary is more complex, and it might end up overfitting your data. So you want a simple decision boundary that can hopefully learn from your data and not just overfit. So overfitting is essentially fitting the data more than is warranted. So what happens is that if your model overfits, it means like it will work perfectly. Your model will work well for your training data, but it will perform very poorly in your test data. And the most important thing, like I said earlier, is that your model has to work very well for your test data, or work better with your test data than training data. And so this graph here just shows like some data points. And so this is an example of a fitting. So essentially this is your training data. So this fits your training data properly, but it wouldn't work well with your test data. So you want something simple like this that can learn from your training data, and hopefully it will perform well when given the test data. And so this graph just describes underfitting and overfitting. So underfitting is when a model is too simple, and so both the training and test errors are large. But overfitting is when the model is too complex, and test errors are large, and the training error is small. So you want to make sure you don't overfit and also you don't underfit. So this slide just shows some notes about overfitting. So overfitting results in models that are more complex than necessary. So again, you don't want something that is too complex or that understands your training too much and doesn't perform well on your test data. Any questions so far?
Is there a good sort of standard for how much data you should use for training and how much you should use for testing?
People use different methods, but I think the more data you have, the better to train. That way, the more data you have to train, the better. More data is always better, yeah. So here, if we're given two classifiers and we want to choose which one of them to use for future predictions, can we use training accuracy to choose between them? What? No? Okay. Everybody know why? Say that again.
They might work well in training, but not well in testing.
Okay. Okay. Yeah, so the answer is no. You guys are right. Yeah. So again, the most important thing is your test accuracy. And so even though it works well on training, you want to make sure that it performs well in tests.
Is there a way to gauge how much of the training accuracy is a result of overfitting versus
Yeah, but I think there are ways, yeah.
What is the 1 minus n mean? The C2 equals 1 minus.
I think NN is decision tree. Neural networks. So these are different classifiers. So they're comparing different classifiers. Yeah.
I think it's one layer neural network, but not.
Say that again.
I think it's like one layer neural network, but I'm not like completely sure.
Yeah, maybe. Yeah.
I think it's one nearest neighbor.
One nearest. Yeah. But I think the point is that they're comparing two classifiers. I got this slide from somewhere, so I'm not 100% sure about the NN, and I can check that. But the point here is that they're comparing two classifiers. Okay. Any questions so far? Okay. So we're going to talk about cross-validation here. So previously we talked about splitting the data between train and test. But sometimes maybe you don't have enough data to split between train and test. And so you can use cross-validation. So cross-validation, essentially you split the data into n equal size parts. And you report the average accuracy between those parts. And we'll see an example. So here you have like your full data set. So in the past, we split it into training and test. But here we're going to have different partitions. So you split the first partition into training and test. And then the second partition, you choose a different portion for test and different portion for training. And you do the same for the other partition. And then you test the performance of each of these, and then you want to get the average of all of this. And so they're different. This is 3-fold cross-validation. People do 5-fold cross-validation or even 10-fold cross-validation.
How much more accurate, or is it like 5-fold or 10-fold more accurate?
I think it depends on the data set. People just use different ones, and then you see which one works best. Yeah, but I think 5-fold is more popular. I can't tell you why, but 5-fold is more popular. Yeah. So essentially, cross-validation generates an approximate estimate of how well the classifier will do on unseen data. And so averaging over the different partitions is more robust than just using a single train and validate. So usually, if you have a large data set, sorry.
You go to the last slide real quick. So is this saying that when you do the cross-validation, you never reuse data, or is it just a way of showing like 5 random selections?
Say that again.
Like by showing the different segments, it kind of implies that when you do the cross-validation, you're never reusing data. But like you could also just do 5 random samplings, which has the potential to reuse data, but it's still random.
So yeah. So
What is this trying to say?
So I think this is trying to say that you're using different portions of the data for test and training. So like the first partition uses a different portion for test, a different portion for training, and then the second one uses a different one. So essentially you want to cover the whole data. So that's the point here, that each of these partitions uses a different part of the data for test and training.
Why can't you just randomly shuffle the data in the beginning and just use whatever your testing thing said?
I mean, you could, but I think part of this is that if you don't have a large data set, and cross-validation is good if you don't have a large data set. And there are cases where you can actually shuffle like for cross-validation, and we'll see that in a few slides.
I think that's what you do. You shuffle it in the beginning, split it into end of K different folds.
What's the difference between why do you need to split it?
Let's say that again.
What's the point of splitting it if we're shuffling it in the beginning and then just taking the portion for it?
Because you know you're trying to use different test data.
You're using all of your data as tests.
Yeah, but we're shuffling it in the beginning, so we should have a random distribution.
So you're basically taking K random partitions in the beginning, and then using one of these partitions as tests every round, and combining the rest as your training.
But if we're shuffling in the beginning, isn't that already accomplished that? If we're shuffling in the beginning and we're using we're using the first 20% as training data, the rest 80% as testing data. I mean, other way around. Then we're going to be using every part of the data for. Like, why don't we just split up into partitions after shuffling?
Split into partitions before, very.
So what are you trying to say now?
I still don't understand the point of splitting into partitions if we're shuffling the data.
So I think the idea is that, like I said, you use different portions for testing and different portions for training, and then you average all of it, as opposed to just
Oh, so we're training and testing like
multiple times, and then you get the average.
So if we're trying to learn a decision tree here, if we do 3 forward, might we get do we get actually 3 different models here? In that case, how would we actually say the overall performance of the algorithm we're using or the model we actually learned?
So I think in the end, one of the important things is that once you run your models on these different splits, you can now average all of them and get like.
Yeah, but what if, because we're training the model using different training data sets. So what if each training data set tell us a different model, or maybe the model are not exactly the same? For example, if the first condition using attribute 1 as the root null, and then the second condition tell me another attribute to be the root null.
Okay.
How would we be able to average those performance and tell us how well the model is performing on average?
That's why we shop in the beginning, right? That would take care of it.
But if you're using different training data, you could potentially learn different models. So at the very end, you're using all of your training data. You're using all of your data to make your model. Then what's the point of separating training data from testing data? You're basically you're trying out your data on different test data. So you're basically like making use of all of your data so that you know how it will perform on any other test data. But the model wouldn't be the same. They might be different. Yeah, they might be different. They would. And then how will you tell so we're trying to evaluate how well the model is performing, right? Yeah. But all those 3 different statistics are performing on 3 different models. Yeah. So we cannot tell which model is doing well, which one is not, right? You can say on average, if I use whatever decision tree on my training data, this is what my test area. So then you take all of your data and then you want to do
Okay. Any other questions on cross validation, or what we just talked about? Yeah.
So would this procedure make K different models?
Say that again.
So if we did this, wouldn't that give us K different models?
What?
Then how do we pick which one to bring to the field?
Which one to do what?
Which of these K models then do we bring to the field?
So I think in the end we want to average all of them, right?
You just average all.
Yeah.
I think in the end you just build a model with everything.
Yeah, you're not using this case selection. You're just using it to test and see how accurate on average this model is on test.
And you can actually have multiple trials of k-fold cross validation. So this k just means it could be 3 or 5-fold, and so you can randomize the data set before you do the cross validation, and then you can calculate the average. You can also do the same thing and test each candidate learner on the same training and test split to see which one works best. And you can compute the learning curve for each of these training testing split. Any other questions on cross-validation?
So, where do you, in the second point, the T statistic,
Good.
paired T test, how would you use a paired T test to evaluate two different models?
We'll talk about paired t-test in a few slides. Yeah. So here we'll talk about hypothesis testing. So here you want to show that hypothesis H is true based on your data. And so an example is if your classifier A and B are different. And the null hypothesis is the contrary to what you want to show. And so, and HO here just shows that, I don't know if you can see my cursor, but HO defines a distribution over some statistics. So an example is the distribution over the difference in accuracy between A and B. And so you want to select a significant value, and you want to show that if your, so if your hypothesis is less than a certain significant value, then you want to reject it. So in this slide, we're going to talk about paired t-test. So a paired t-test is used to compare two population means. So an example is the before and after observation of the same subjects. So this slide just shows some procedures for carrying out paired t-test. So you can calculate the difference between the two observations on each pair. You can calculate the mean difference, calculate the standard deviation of the differences, calculate the error of the mean difference, and calculate the t-statistics. So this is an example of the paired t-test. So the question is the downtimes measured in hours for computer systems in 6 branches of a major bank were recorded for year 1 and year 2. And you want to compute the test statistics for the paired t-test. And so this just shows the number of branches, year 1, year 2, and the difference in year 1 and year 2, and the squared difference. And so to compute the paired t-test, the sample size in this case is 6. The sum of difference is 37. The sum of the squared difference is 419. And we got this from this table here. And the mean of the case-wise differences is 6.1666. The standard deviation is calculated this way, and it's 6.177. And the test statistics is calculated using this formula, which is 2.445. Any question about how that is calculated? Or?
What are we testing with this paired t-test?
So it's just comparing two population means.
And what does the value tell us? What's our conclusion after doing a paired t-test?
I'll have to check that. I'm not 100% sure about that. Yeah.
Is it saying that if this t statistic is significant different from 0, then we have 2 different populations with different?
Okay.
That might be the case. Yeah.
And this, so this is the last test we're going to talk about, Magnum Ass Test. And this test is used, it's often used for the situation where one tests for the presence of one or absence of something and variable A is the state at the first observation, and variable B is the state of the second observation. So this is an alternative to cross-validation. So we want to divide the sample data into training and test. I want to train algorithm A and B on the training. And we want to record how each of them performed on the test data. So this here shows, So this table here just shows the examples that were misclassified by both algorithms. And the example that was misclassified by A but not by B. And the examples misclassified by B but not by A. And the examples misclassified by neither of them. Where all of them add up to N, which is the total number. And so the formula down here just calculates the measure of deviation from the expected counts for this, yeah. And so that's what I have here.
Could you go back to the first nickname? Yeah, that one.
And we'll post the slides on the website. Any questions? Okay, we'll have visitations this evening at 6:30, and then tomorrow at 5:30. Evangeline, do you know how to turn this off? Yeah. Today? Yeah. He won't be around.
He won't be around.
Yeah.
Is there any other?
Let me see. That's good.
Is he out of town?
He's out of town, so I'm not sure about this week. Well, I think he'll be around on Thursday, so yeah. Let me see. So Thursday, 4:30 to 5:30. Yeah.
I see. Okay.
So he will teach the class on Thursday. Yeah.
Okay. I wanted to ask a question actually about the quiz.
Yeah. What
One
about?
of the questions, I guess one of the questions correctly, but I'm not sure I understand it, and I wanted to just clarify whether I understood it. That was my question that I wanted to ask.
Oh, okay. What's? Trying to figure out what the quiz is.
It's like on Canvas.
On Canvas. Yeah.
Wait, Huang, do you want to ask about the quiz question?
So
I'm asking about the quiz question.
I'm not seeing the quiz yet. Yeah. What was the?
It was like the first question about the hypothesis space of the function. Yeah, this one. I guessed it correctly, but I don't think I
Let me see if someone has office hours. So you can... Today's Tuesday.
Oh, okay.
So if you
I'll
go to
okay, like in an hour.
yeah,
Okay.
if you go to the, you know where this is, right?
Yes, this is a recitation. Okay,
Yeah.
thank you.
Okay. Yeah, that was sharp. Yeah. Yeah. I didn't want to. Yeah. Oh, yeah. Let me send it to you.
Andy, so like for my office hours,
So-
do you find any space or like
I
should
think
I like?
you have to move your time, though.
That's fine. Like as long as I have a list of timings, I can like pick one.
So maybe I'll email you the times,
Yeah, that'll be better.
and then yeah. So I'll email you the times for Levine and then for the other place.
Yeah, Levine, if you have, that'll be better.
Okay.
Levine, I can do 1 hours also. But if I'm doing there, I would prefer 1-2 hours. That I don't want to go there and waste like 10 minutes going and coming.
Yeah.
By the way, where are the solutions for the homework one?
Yeah, like I have roughly prepared them. I will send them out
Yeah, cool.
in a day or two, maybe most probably tomorrow. And who is going to grade homework one? Same people.
It's
So just
better if the same
So
people
I don't
do
know. I
because-
think Dan didn't want that. He wanted different people to do it. So I don't know. It's something we
I
can
think he
talk
wanted it because so that no one will have continuous work for a week or two.
about. Yeah.
That's he want to split it.
the
But that's not fair. That's not like sensible because it'll take more time for the other to figure out what all were the intentions behind
Yeah.
the homework one.
Yeah.
Or if
so I don't want to like so two people test like grading 146 homeworks.
and one more suggestion, like if
So this I'm gonna add more, but I think if some time doesn't work for you, just let us know. We can move it around. I think so. For the testing, there'll be 2 people each for writing the
testing
homework.
is the guy who's writing the answer solutions, or only testing.
So these guys write the homework, right? And then these guys test it to see
If the homework,
if it works and how long it takes and give feedback.
yeah.
And
I
then these
think
guys
then
trade.
these two should be merged.
The grading
Because
and
like yeah, at least because it's not much work testing the homework.
it depends. I don't know. So the homework this time took what, 4 hours? Yeah,
4 hours too.
it took 4 hours. Well, at least 4 hours. That's what they said. And I'm assuming that later homeworks might take longer. So I don't know that it's fair that they will essentially be doing more work, like doing this, and this is like 150 students, so it'll be a lot.
Okay.
I mean, we can merge it at some point, but I think
So
splitting it is a
Let's
good
discuss
idea.
that on Thursday when
Yeah.
that comes.
Yeah. And then let me email you the times.
Or maybe it would be better if we get a shared calendar link to all of them. Then you can just
To all of what?
if we can share our calendars with you.
And this
Mhm.
Friday I won't be able to. Yes.
currently I'm only holding one officer. One hour.
What's the email for the group?
TAs.
Sys 19.
Sys 5 and 9. Sys hyphen TAs. No, TAs hyphen Sys 5 and 9.
Oh, is it? Oh, okay.
It's CIS what?
No, it's TAs. Yes. Nope.
Let me get it.
Okay, I will see you guys.
Okay.
CS 5 and 9 hyphen TAs. Okay.
So that is for Levin. And then let me send for. So you have the availability for Levin on Walnut Street. Yeah. So whichever one works for you, like, yeah. So you don't have any hours yet?
Me?
Any TA hours? You don't have it? I wonder what the other TAs would have, what questions they've had during the TA hours regarding. Have you had any yet? The TAs, did anybody ask questions on Friday? What kind of questions are they asking? Nothing on the homework? Oh, yeah.
Someone posted asking if they get one more day. Just got released. You have 2 weeks.
And then will you guys be around this evening? For the presentation?
Oh, I can't be.
Will you be around? Today for the presentation? Yeah.
The station one.
Presentation? So I have to do the slides for decision tree. I started it, I'll finish it this afternoon. We need a lot of help.
You need someone to help you type the slides?
No, just